Hello everyone and welcome. In this video, we're going to be building a shortest path finder in Python. So basically the way this works is I have this maze right here. It has a starting position and it has an ending position. And then it has these obstacles, which are denoted by the hashtags, and it has empty coordinates. Now, when I run this code, this is going to print a maze which has X's here, denoting the shortest path from the beginning of the maze, or the starting coordinate, and the ending coordinate right here. If I change the starting coordinate to be a little bit more over here and I run this code again, this is going to give me the new shortest path. Now, this isn't a completely a beginner project, it's more intermediate. You should be comfortable writing in Python at least a little bit, but other than that, it's not going to have restrictions. It's going to run on your terminal, as you can see, and I'm going to explain everything thoroughly as I go along. I'm also going to be explaining something called a breadth first search algorithm, which is the algorithm that we're actually going to be using to find the shortest path. If you're not familiar with that, don't worry, because I'm going to explain it thoroughly as well. So let's get right into it. I have this other file right here which only has my maze, and let's start building the project. Now the first thing I'm going to do is I'm going to create a function that allows us to display the maze onto our terminal. So I'm going to say define display maze. This is going to take in the maze, and in here I'm going to create a variable called maze row. It's going to equal an empty string in the beginning. And for each row on our maze, keep in mind that our maze is a list with a bunch of lists inside, and all of those lists are going to be a row. And for each of those rows, I'm going to get each element of that row, append it to this maze row variable right here, and display that row. So in order to do that, I'm going to say for row in the maze, and for tile or coordinate or whatever you want to call it in the row, I'm going to add to the maze row right here. So maze row plus equals first an empty string, which is going to act as a separator between the symbols or the tiles or whatever you want to call it, plus the tile itself. And then I'm going to print the maze row like so, and I'm going to reset the maze row. So maze row equals an empty string like so. So hopefully this is going to display our maze for us. Let's say display maze with the maze. And if I run this, okay, so it's working correctly. It displays the maze, it has the obstacles, it has the empty coordinates, and then it has the start and the end right here. So now I'm going to create another function that allows us to find the start node of the maze. So I'm going to say here, define find start, like so. And this is going to take in the maze. And in here, I'm going to say for row in range length of maze. So in range from 0 to the length of the maze. And then for call in range len of maze at the coordinate row. So from 0 to the length of the row, I'm going to say if the maze at the row and call is equal to the start, so if it's equal to s, then I'm going to return a tuple with the coordinates of the start, so row and call. And actually, this is looking a bit ugly, so let me say maze size, like so, is going to be the length of the maze. And I'm going to substitute that in here, so maze size, like so. And I'm going to do the same thing for the row. So row size is going to be the length of the maze at the coordinates 0. So we're going to get the first row of the maze, and then we're going to get the length of that row. And I'm going to paste it in here. So row size. Because if we say for row in range length of maze, then we're recalculating the length of the maze each time we go through an iteration of this loop. So if we do this down here or up here, we're going to be calculating the maze size only once and not recalculating it every time we go through another iteration. So it's much more efficient this way. And okay, so let's try to find our start. So let's say start node equals find start, like so. and we're going to pass in the maze, and let's print the start node, like so. So let me run this, and this is going to give me 0, 6. So let's go up here and 0, 1, 2, 3, 4, 5, 6. Okay, it's perfect. Now I'm going to create another, actually instead of creating another function, I'm going to reuse this function right here with the end. So instead of saying find start, I'm going to say find node, and I'm going to pass in the node right here. Now, instead of checking if this is equal to s, I'm going to check if this is equal to the node. And the node can be either equal to s or to x, depending on which node we're trying to find. So find node, and the end node is going to be find node with the maze, and the node is going to be x, and up here the node is going to be an s. Okay, so using this this function right here, we can find both the end and the start. So let's run this, and it's going to give us first the end and then the first the start and then the end. Okay, perfect. Now, in order to actually find the shortest path from the start to the end in my maze, I need to transform my maze into something called a graph. So a graph is basically a structure that allows us to represent the connections between nodes. So I'm referring to each of these coordinates or each of these symbols as nodes of our maze. And let me actually open here the whiteboard, and I'm going to explain to you what a graph is. So imagine that you have 4 cities. You have A, B, C, and D. And C, B, and D are connected to city A, but they're not connected between themselves. So C is not connected to D, and D is not connected to B. So this is what's called a graph. This is a structure that represents the connections between the cities A, B, C, and D. Now, in code, there are different ways to, represent a graph. You can represent a graph using an adjacency list, using an adjacency matrix, and other formulas as well. What I'm going to be using is going to be an adjacency list. Adjacency list, which is actually going to be a dictionary, but yeah, I call it an adjacency list. So an adjacency list for this graph in particular would be, for example, A is connected to B, C, and D. B is only connected to A. C is also only connected to A, and D is also only connected to A. So this would be an adjacency list for this graph. It has each city of the graph, so A, B, C, and D, and then it has a list with the cities that are connected to that city. So A is connected to B, C, and D, B is connected to A, C to A, and D to A. So that's an adjacency list. So for our maze right here, basically what we're going to have is we're going to go to each empty node. I call this a node. This is a coordinate or a symbol, whatever, but it's called a node when you're talking about graphs. So we're going to go to each empty node, and we're going to see which of the adjacent nodes we can travel to from that node. So for this node, we have 4 adjacent nodes, this one, this one, this one, and this one. But those 3 have obstacles, so we can't go to them. We only have this node that we can actually travel to, from this node. So the adjacency list of this node is going to be this node. And I'm going to do this in coordinates. So let's actually create a function to find the adjacency list that represents this maze. So I'm going to say define transform to graph, and I'm going to pass in the maze. Now in here, I'm going to create an empty dictionary, which is going to be the actual graph. And I'm going to say maze size is equal to the length of the maze, and the row size is equal to the length of the maze at the coordinate 0. And now I'm going to say for row in the range of maze size, like so, and for col in range row size, like so. I'm going to check if the node at these coordinates is empty. So if the maze maze at the row and the call is not equal to an obstacle, so if it is either an empty string, the end, or the start, I'm going to create a list here called adjacency nodes, which is going to be empty in the beginning, and I'm going to do a bit of if and else's. So I'm going to check in every direction if the node that we are currently looking at is empty or not. So I'm going to say if row plus 1 is smaller than the maze size, and the maze at the row plus 1 and the call is not equal to an obstacle. So here, basically what I'm checking is if going up a row doesn't take us out of the bounds of the maze, so if it is smaller than the maze size, and the maze at the row plus 1 and the column is not an obstacle, then we're going down on the maze, right? Because we're increasing the row. And that means that the node at these coordinates is going to be, what do you call it, a valid node in the adjacent nodes of the current node that we're looking at. So we're going to say adjacent nodes dot append, and we're going to append these coordinates, so row plus 1 and the call, like so. And now we're going to do this in every direction. So I'm going to say if row minus 1 is greater than or equal to 0, so if going if going up a row doesn't take us out of the bound of the array, and the maze at the row minus 1 and the call is not equal to an obstacle, then this is a valid node. Let's say adjacency nodes dot append the coordinates row minus 1 and call. And this, the direction we're going is up. And I'm going to say if, let me just check here my cheat sheet. So if call plus 1 minus the row size, sorry, if call plus 1 is smaller than the row size, not minus row size, and the maze at the row and call plus 1 like so is not equal to an obstacle, then this is valid. Let's say adjacency nodes dot append the call plus 1 and the row. And here we are going to the right. And the last one is going to be if the call minus 1 is greater than or equal to 0, and the maze at the row and call minus 1 is not an obstacle, then we're going left. And this is a valid node, so adjacency nodes dot append the row and the call minus 1. Okay, so let me just see if I didn't get anything wrong. So down, up, right, and left seems like everything is correct. And now I'm going to add the adjacency nodes to our graph. I'm going to say graph at the row and call is going to be the adjacency nodes. Okay, and now down here, I'm just going to return the graph. Okay, so now we have all of the auxiliary functions that we need. We have a function that allows us to display the maze onto the terminal, a function that allows us to find the start and the end node in coordinates, and a function that allows us to transform the maze into a graph that we can then manipulate. This graph is going to be a dictionary in which the keys are going to be the coordinates of the empty nodes of our maze, and the values are going to be lists with the empty neighbors of those nodes. So now I'm actually going to explain how the breadth first search algorithm works and how we can find the shortest path in this maze. So I'm going to go here to my whiteboard. Let me first erase all of this, just so that we have this a little bit more cleaned up. I'm going to grab my pen and I'm going to create here a mini 3x3 maze. It's going to have two obstacles here and here. This is going to be the start, this is going to be the end. And let me just put numbers on the nodes, so 1, 2, 3, 4, and 5. So in order to find the shortest path, we're going to use a data structure called a queue. And this follows a principle called FIFO, which stands for first in, first out. So the queue is a data structure in which the nodes or the elements of the queue are processed by the order in which they're added to the queue. That's why first in, first out. So the first element that you put in the queue is going to be the first element that you're going to get out of the queue and process. Now, I do have a whole video about the queue data structure if you want to know more about it in depth, but the explanation that I'm going to give here is going to give you the basics that you need to understand the breadth first search algorithm. So we're going to have a queue here, and first I'm going to add my start node. Now we're going to remove the elements that are in the queue in order, and we're going to get the neighbors of those elements. So now I'm going to get the neighbors of the start, which is going to be 1 and 3. And now 1, I put it in my list first, or in my queue first. So I'm going to take it out first, and I'm going to get its neighbors. So I'm left with 3 in the beginning, and the neighbors of 1, which is 2. Now I'm going to get 3. I'm going to get its neighbors. 2 is going to go to the first position. And the neighbors of 3, which is 4, are going to go to the end of the queue. Then I'm going to get the neighbors of 2, which, well, don't exist, right? Because I only have either 1, which I already visited, or an obstacle. And I don't want any of those to get in my queue, so I go to the neighbors of 4, which is 5, and the neighbors of 5, which is the end node. Now, when we reach the end node, we are guaranteed to have found the shortest path that leads to that node. And why? Well, that's because every time we add something to the queue, we're adding one more node, right? So at one certain point in the queue, we only have elements that have a certain length or less, right? We only have paths that have a certain length or less. So when we go to the neighbors of the start, we have paths that have 2 of length or less. When we go to the neighbors of the neighbors, we have paths that have length 3 or less. So when we get to the end node, we know that we found the shortest path, or the path that has that length or less, and that contains the shortest node. So I hope that's easy to understand. I know it's not completely trivial, but it's not difficult to understand either. So I hope it was easy to understand. Let's actually implement this into the code. So the first thing I'm going to do is I'm going to go up here and I'm going to import the queue data structure. So I'm going to say from queue import the queue, like so. So now that we've done that, let's scroll back down and let's create here a function called solve maze, like so. And this is going to take in the maze and the maze graph. So the first thing I'm going to do here is I'm going to create a list called visited. Now, every time we visit a new node, we're going to add it to this visited list so that we make sure that when we're processing the neighbors of the nodes, we're not reprocessing nodes that we've already processed, right? So each time we get a new node, we add to this visited list. Then we check if the neighbors of that node are already visited. If they are, we're not going to visit them again. Okay, then I'm going to have the start path. The start path is going to contain the start node. And I actually forgot to pass that in here. So we're going to pass in the start node and also the end node, like so. And then we're going to create our queue. So queue equals queue, like so. And we're going to first add this, this path right here that only contains the start node to our queue. So in order to do that, say queue.put the start, oh my God, I can't write this, start path, like so. Okay, now we're actually going to go into the breadth first search algorithm. So let me say while not queue.empty. So while the queue is not empty, we're going to keep applying the algorithm. We're going to say path equals queue.get. So the path is going to be the first element of the queue. And the neighbors like so, is going to be the maze graph at the path -1. So we're going to get the last node of the path, and we're going to calculate the neighbors of that node based on the graph representation of the maze, and we're going to process those nodes. So I'm going to say for n in neighbors, like so. I'm going to say if the n is equal to the end node, then we're done, right? We found the end node and we found the shortest path. So I'm going to say, so for coordinate in the path, I'm going to say row call equals coordinate. And then the maze at the row call like this is going to be an x. So we're going to substitute basically every node of the path with an x so that we can see the shortest path. And in the end, I'm just going to say return the maze, like so. Now, otherwise, we need to process this node. I'm going to say if neighbor not in visited. So if we haven't visited this node yet, I'm going to say visited.append the neighbor. And the new path is going to be the current path plus the neighbor, like so. And now we're going to put the new path in the queue. So queue.put the new path. And this is going to conclude our algorithm. So let's go through this one more time. So first we create a visited list, which is going to allow us to make sure that we're not visiting a node twice or more than once. And we're going to create a start path. Now in the beginning, we're only going to have the start node in the path. Then we're going to create a queue, and we're going to put the first path with the start node in the queue. Now, while the queue is not empty, we're going to successfully remove elements from the queue with queue.get, and we're going to store them in path. And also, we're going to get the neighbors of the last node of the path. So the last node that we've added to the path, we're going to get the neighbors of that node, and we're going to process those neighbors. So for each neighbor in neighbor, if we found our end node, we're going to add the path to the maze with x's. We're going to denote the path inside of the maze by writing x's in those coordinates. And then we're going to return the solved maze. Otherwise, if the neighbor is not in visited, then we're going to append the neighbor to visited to make sure we don't visit it again. We're going to create a new path, which is going to be the current path plus the node. And we're going to put the new path inside of the queue. Now, if the neighbor is in the visited list, we're not going to do anything, right? We're just going to continue. And this basically concludes our project. Let's actually allow the user to see this. So I'm going to say solved maze is equal to solved maze. And this is going to take in the maze graph. I'm going to create here maze graph is going to be transformed to graph the maze. And then we're going to pass the maze graph in here. And then we need the start node, like so, and the end node, like so. And if I run this now, let's see if this works. Oops, we got a key error, so let me just see what's wrong here. Okay, I apologize for the mistake, guys, but here instead of call plus 1 and row, this needs to be row and call plus 1. Okay, so if I run this now, it should work. Let's see if it does. And okay, it does work. It goes from the starting position to the end position and finds the shortest path. Now let me change here the start position to be over here, for example, and see if this still gets the shortest path. Let me run it. And yeah, it gets the shortest path. And now let's change this to be, for example, over here. And it still gets the shortest path. Okay. And let's just one more. Let's put it over here, for example, the start. And let's run this. And it found the shortest path. So this is it for the project. Thank you guys so much for watching. If there's something you didn't understand, please don't hesitate to ask in the comments. I know this could be a bit confusing if you've never seen this kind of thing before. But if you enjoyed the project, please like and subscribe to support the channel. Thank you so much for watching, and I'll see you in the next one.